Hello everyone, welcome back. We're starting chapter 24 today. And as much as I know you've all enjoyed the derivations on electric fields, whether they be the calculus method or the Gauss's law method, we are going to depart from the electric fields for a while and explore an alternative to measuring these systems. Specifically, what we want to do is we want to go from the electric field stuff that we've been doing in the last two chapters. And electric field, one of the reasons why we were struggling a little bit to set up all of the derivations and integration was due to the fact that we had so many infinitesimal charges that had to be added up to produce a vector. And the vectors have those field components. And so what we want to do is we want to see if we can sort of take all of that information and condense it down into a scalar quantity. Except that it's not going to be as simple as just asking for the magnitude of the electric field. There is a new term that we're going to start using, which we are going to call electric potential. And the word there, potential, that is something that we have all heard before. Specifically back in Physics 1, we had potential energy. And as much as we might be tempted to think that this is going to be a potential energy term, it is not. There is such a thing as an electric potential energy, just like there is a gravity potential energy, there's a spring potential energy, there's even chemical potential energy. So there's lots of different kinds of potential energy that are out there. But what we're going to do is we're going to stop right at the term potential. So these two terms are not the same thing. Even though they sound the same, even though they have the same words in them, potential energy is energy. As such, energy will be measured in joules. Energy can be transferred, and transformed. I was trying to say both words at the same time. Energy can be transferred or transformed. But electric potential, this is a completely new term. We have not seen this before in Physics 1. And so what we need to do is come up with a definition as to what electric potential is, why it's different from potential energy, and then see if the two are related in any way. And I'm going to test everyone on this little tidbit here. I'm going to ask for potential energy at some point, and if I do, you will see the two words potential and energy together in the same statement. Otherwise, if I just say the term potential and we don't see the word energy anywhere with it, then we are referring to this new term that we call electric potential. And this is the definition that our book and our author have for electric potential. So I'll just go ahead and put this on the screen here, and then we can start working our way through some of the math related to this topic. So we say that when an electrostatic force, so these would be the electric forces that we were studying back in chapter 21, when an electrostatic force acts on a charge, Actually, we'll say a charged particle. We can assign an electric potential. Energy to the system. Well, here we're using potential energy. Why are we using potential energy? Well, we're going to start from an idea that we're already familiar with. We already know what potential energy is. In this case, it just happens to be an electric form of potential energy. But we know what potential energy is. This is an energy that is basically stored in the system that will have the potential to do work at a later time. So let's see what that means for our charged particles. If I have a charged particle, in this case we'll just have a positively charged particle, and if we place that charged particle inside of an electric field, that particle will then experience an electric force as a result. And this comes from the very beginnings of chapter 22. But now that force, once it's applied to our particle, is going to start displacing that particle. We're going to move that particle. Oops, I wanted a different color there. So we're going to move that particle. We will start at some initial position that we will call R0, and we will end at some final position that we will call R final. And so the displacement that we carry out is the difference in the two positions. But let's see, what should we call it? We could just call it a displacement of d if we wanted to. So d would be the difference in R final and R initial. But we should remember from Physics 1 that anytime a force is applied to a displacement, there is work done. Specifically, that force displacement vector combination needs to be in the dot product form, because work is technically a scalar, and the only way that we can take the product of two vectors and turn it into a scalar quantity is if we're using the dot product. But this is to our benefit, because this now tells us how much work any given force can do over a displacement, because we need that force to have components in the direction of d, and that's what our angle relationship tells us. Okay, well, in this case, the angle relationship between the two vectors, f and d, is 0. They're running parallel to each other. And so the only thing that I have for work done in this system is Fd. Well, let's take that knowledge combined with what we know about that force. We know that that force is a result of the charge, Q, being placed inside of the electric field of E. And so we now have Q, E, and D. And if we backtrack that, we now have our charge, Q, times the dot product of the electric field and the displacement vector. And that is the amount of work done. But this is just work. We said that we want to relate this to the potential energy in the system. Okay, well, potential energy, if we go back to our Physics 1 discussion on energy, we know that any conservation of energy expression says the energy that we start with is the energy that we end with. And we're going to assume in this case that we're not losing any energy due to friction or thermal heat loss. And so the change in the kinetic energy and the change in the potential energy for the system will have to be equal and opposite to one another. And we can actually show that just by rearranging some of the terms. I'm going to subtract the initial kinetic energy from each side, and I'll subtract the final potential energy from each side. And the reason for doing that is just so that we can get the potential terms and the kinetic terms together on the same sides. Now over here I have final minus initial. By definition, that is a delta statement. That is the change in kinetic energy. But over here I have the opposite. I have initial minus final. If I were to multiply everything on the left by a -1, that would change the signs, and I would then have a delta U statement. And so if I apply a negative, then I get a delta U. And so now I have what was just mentioned about a minute ago, that any change in the kinetic energy will have to be equal and opposite to the change in the potential energy for the system. And lastly, from Physics 1, we learned that the net work done by any collection of forces in a system will be responsible for changing the kinetic energy. But if the kinetic energy has to change in an equal and opposite amount to the potential energy, then any work that is done is also responsible for changing the potential energy. And we can bring that idea back up here. If the electric force is the only force in the system that is providing work, then we now have the network in the system, and we can apply that to the change in the potential energy for the system. Now we're gonna hold off on this part for just a moment, because what I want to do is I want to take that expression, which is the work that's being done, and I'm going to set that equal to the change in the potential energy. And our author at this point decides to trade the minus sign over to the other side. And so what we'll have now is negative work equals the positive change in the potential energy. So this is final minus initial. And what this minus sign on the work does is it implies that the system is doing the work. Okay, so system is doing work. So not the particle. But that should be pretty evident, because we need the electric field of the system to interact with the charge to produce that force, and we need that force to produce the work. All right. So now what? Well, what we're going to do is we're going to take that charged particle, which is being acted on by that force F, and we're just going to let it travel out as far as it can possibly go. So we want to let this particle go all the way out to infinity. And then we're going to bring it back. Now, why do this? Well, eventually what we're trying to do is we're trying to come up with an expression that will tell us what the potential energy of our particle is. But I need a specific location if I'm going to measure that potential energy. Our potential energy can change as we move between two locations, but that's not really enough information. Right now, the best that I can do is I can say that any work that's done will change the potential energy, but it doesn't tell me what the individual values are. It just tells me what the difference is. And so if I had 20 joules of work done in the system, well, how many different ways can you make a difference of 20? It could be 20 and 0, it could be 40 and 20, it could be 180. There's a lot of different combinations that would give us that difference, but we need to specifically figure out at least one of the values, initial or final potential energy, and then we can deduce the other by knowing how much work was done. So why go all the way out to infinity? Well, remember that the whole reason our charge started moving was because it was under the influence of some electric field. And we've seen in multiple cases that if we get far enough from the source of an electric field, that electric field will more than likely go to 0. And if I don't have an electric field, I don't have an electric force. If I don't have an electric force, I can't do work. And if I can't do work, I can't change the potential energy anymore. Which means way out here at infinity, my system would have 0 potential. In other words, the system would no longer have the potential to continue doing work. And so the potential energy would be 0. And we're going to go ahead and let that be the initial potential energy for our system. And that way, as we travel back, so we're going to start way out at infinity, and we're going to travel back to this location right here. We're going to let that be the final potential energy. And it's going to take some work for us to bring that charged particle back in. And you'll see now that that amount of work is in fact negative, because our force and our displacement vectors are pointing in opposing directions now. We would end up with a cosine 180 relationship between these two. But this is okay, because the work that's done is going to equal the change in those potential energies. And because we started way out at infinity, the initial potential energy was 0, which means that the final potential energy is going to be equal to the amount of work that was required to bring it into the system. Well, so how does this fit in with electric potential? So now we're going to define that term of electric potential. Now that we know how to define the potential energy of the system, now we're going to move on to the potential. So we're going to define this new term that allows us to define the potential energy of the system by taking advantage of the charge particle and where it is currently located. And it's a pretty straightforward term. The electric potential, we are going to denote that with the symbol of V. And it's at this point most people start to recognize the electric potential by its more common name, which is voltage. So V for voltage makes a lot of sense. And the units for electric potential are going to be the volt, hence the more common name of voltage. So how does this voltage, aka electric potential, compare to the potential energy of the system? If we look back at the diagram, remember that we could have this electric field without the electric charge being present. So that electric field is there, whether or not the charge is there. But we need that charge to be present if we want a force. Okay, we have to have that charge field combination to produce the force. And we need that force to provide the work. So what would happen to our potential energy expression if we removed the charge? Well, I guess that would mean that there would no longer be a potential energy. There would just be a potential. So here's how we're going to define electric potential. Electric potential would be what you get if you take your potential energy and factor out the charge. And that's pretty much it. So the two terms are related to each other. It's just that one of them includes the value of the charge, the other one does not. Now the potential energy, as we remember, had units of joules. The electric potential, or the voltage, I'm going to try my best to use the term voltage from here on out, just so we don't have any confusion between the two. But the book and some of the homework problems and test problems may choose to use the term electric potential. And so we need to be very careful when we read those statements. If it says potential, they mean voltage. If it says potential energy, well, there's the key word, energy. That's when you get to use potential energy. But we have volts over here. And the units of charge, those were coulombs. So a coulomb volt would be a joule, or we could say that a volt is a joule per coulomb. So just looking at equivalent units there, in case we need to switch them around for any reason. Well, if our potential can be represented as this ratio of potential energy over charge, we already know that potential energy can change. And first rule of algebra is what you do to one side, you have to do to the other. So if I have a changing term of potential energy, that means that there has to be a changing electric potential throughout the system. The change in our potential energy up above, we said that that was negative the amount of work done. But since we're dividing the change in potential by Q, we have to divide by Q on this side as well. And now we can write V final minus V initial equals negative work over Q. Now we're using volts to define the electric potential, but this means that we now have a new way of defining the units of electric field. So let's take what we had for electric field. Let's see here. Electric field came from force over charge, so that's newtons per coulomb. And our volts are in units of joules per coulomb. So let's see here. We've got a joule is a Newton meter. And so the unit, I'm sorry, this is not a product, this should be an equal sign. So the unit for a volt is not that far off from the unit that we're currently using for the electric field. The only thing that we're missing is a meter unit. And what we can do in that case is we can introduce the necessary unit as long as we introduce the necessary term. Meter is going to measure length or displacement. And so what we have now is that the electric potential, oops, came out kind of squiggly. Just by looking at the unit analysis, the electric potential can come from a combination of the electric field times the displacement or the current position in space where you're trying to measure everything. Because all that's required at this point is we could sneak a Q in front of everything, and this turns everything back into work, which is what we had way up at the top here. Work was QED, and it was the change in potential energy. Well, Q times V, that's our potential energy term. The only thing that we're missing to make all of this work out right, keep in mind that potential energy and potential itself are both scalar quantities. Potential energy is a scalar, and we said that we were going to define electric potential as the ratio of potential energy to charge. Charge is also a scalar, so that means that potential has to be a scalar, but electric field and displacement were both vectors. So how do I turn two vectors into a scalar? Well, this brings us right back to the electric field displacement dot product. And so now we've got it. We're like, okay, so we have this new term, electric potential. It's a scalar. Obviously, scalars are going to be easier to work with, but what's the point? Why do we need this this potential term? once we have potential, we can then start asking questions about how much work is done in a system, or even better, how much energy is going to be used up or transferred in a given system. That's always helpful to know. But for anyone that's ever even heard of anything related to electricity, voltage is a very big term. You always see signs that say danger, high voltage. Well, why is it high voltage? Why is it dangerous? We're going to learn that in the upcoming chapters. But before we start applying voltage to electrical systems, specifically in circuits, we need to know how we're going to derive the electric potential in a given system. And right here, we might think, well, isn't that it? Isn't that the only thing that we have to do? And the answer is kind of yes, no. It's a deceptively simple expression. What makes it deceptive is that there's a lot of information that goes into that first term regarding the electric field, as we already know in previous chapters. It caused us quite a bit of heartache trying to derive what those electric fields were going to be, and so the next step is that we're going to have to figure out how we're going to derive the electric potential expression. And so taking this expression works really well if you have a uniform electric field. But we already know from past experience that we don't have a whole lot of uniform electric fields out there. Our electric fields are constantly changing as we move through space, which means that our electric potential is going to be changing as we move through space. So there's more math to come. But for right now, I want to take a break from this force, work, energy discussion, because we now have another bit of unit analysis that we need to discuss. Since we now have electric potential defined as charge times voltage, let's just consider an example of a charge placed into a given electric potential. So we'll say we have an electric potential of 20 volts, and we're going to place a proton inside of that electric potential. And so our proton has a charge of 1.602 10 to the minus 19 coulombs. Once we place that proton in this 20 volt electric potential, what is the amount of potential energy associated with the system? And well, that's not so hard. We're just going to take our charge value and we'll multiply it by the 20 volts. We get out our calculator. 1.602 times 10 to the negative 19 times 20, and this makes for 3.204 times 10 to the negative 18. We need units. Well, we're looking for an energy term, so that's joules. Well, what if I were to tell you that there is a much quicker, much more efficient way of describing the energy associated with this system? Would you rather use that? And as of yet, I have no one that's said no. So let's take the same proton. We're going to stick it into the same electric potential, but instead of using this value right here, why don't we use this value? And when I say 1e, what do I mean? Well, E is the value of the elementary charge, and that's what the charge of the proton is. It is positive 1e. And it's a lot easier to just write out 1e than it is to write out 1.602 10 to the minus 19 anytime we need a proton. If we write things out this way, well, I now have positive 1e times 20 volts. 1 times 20 is 20. And the units that we now have are the elementary charge times the volt, also known as the electron volt. And this is a unit of energy. The electron volt is what you would get if you took the magnitude of the charge of one electron. Well, why are we using an electron? We said it was a proton. Well, what's the magnitude of charge for a proton versus the magnitude of charge for an electron? They're both positive 1e. And so we have the magnitude of one, maybe elementary charge would be better, but that doesn't change the name of the unit. We still call it an electron volt. Or if you're more comfortable, you can just call it an EV, and people will know what you're talking about. So we have 1 elementary charge times 1 volt equals 1 EV. But the true product of our two terms, 1 times 20, was 20. And so we have an energy of 20 EVs. Those 20 EVs are equivalent to the value that we just calculated up here. 20 EVs would be the same as 3.2 times 10 to the negative 18 joules. So how do we convert back and forth between the two units of energy? Well, your conversion factor is hiding right here. E is the elementary charge. So if you were to sneak in the value of E, you would get 1.602 10 to the minus 19 times 20, just like you got right up here. But it is just so much easier and faster to write out the energy in terms of EVs than it is to carry through all the arithmetic and get an energy of joules. Now, the joule is still the standard international unit for energy, and so at some point we'll probably have to convert everything back to joules, but in the meantime, having your energy in EVs is a lot more convenient. In particle physics, it's not uncommon to have an energy associated with a particle that could be mega electron volts or even giga electron volts. We could have a particle that's got an energy value of 5 giga electron volts, and you might be thinking, wow, that's a lot of energy. And for a single particle, yeah, it's a lot of energy, but compare that to things that have energy in our day-to-day lives. We have giga, which is 10 to the 9th, but then you have the electron volt, which is 10 to the negative 19. You've got volts, which, well, that's just one volt. And so now we're getting, what, 1.602 times 10 to the negative 10 joules. That one particle has probably, I'd say, 1/10 of 1/millionth. No, going the wrong way. Yeah, that's about right. About 1/10 of 1/millionth of the amount of energy that a mosquito would have flying around. So not a whole lot of energy, even though it's up there in the giga range. But that is high energy for an individual particle, because now if you start adding up, a couple billion of these particles, you could very well start getting into some pretty energetic systems. But it's these energies of the particles that can be measured, and in turn we can take the energy of certain particles and we can deduce things like the mass of the particle. And so that helps us with identifying what those particles are. All right, let's see what else we can talk about for this first video. So we mentioned that, so up above here, we mentioned that the work that was done in changing the electric potential energy and thus the electric potential for the system was negative. And that's because the system had to do work on the charge. Well, now we need to figure out, how do we get rid of that minus sign? Because the system by itself is not going to just allow the charged particle to spontaneously work against the system. Okay, the system is doing negative work, and so the only way that we can get that charged particle to get to that final position is if we apply our own force. In other words, we have to apply some amount of work that is equal and opposite to the amount of work that was done by the system. So we're going to do the work to move the particle to its final position. The initial position is where the potential would be 0. And so now we're going to switch out the work done by the system for the applied work that we're going to do. And since the initial potential is 0, then the final potential just has to be the applied work that was done. But we could also say that if we moved the charge back over, this would have to be the final potential energy, which takes us back to the basic definition of potential energy. Potential energy is supposed to be energy with the potential to do work, and that's exactly what we're doing. We are putting work into the system to take the potential energy from a non-zero or from a 0 value to a non-zero value. So we are literally putting this energy into the system, and once we have moved, so once we've started back at infinity, and once we have physically moved the charged particle to the final position, the system now has a potential energy, in the amount of QV. So I think this is a good place to stop for this video. We're probably approaching the 1 hour mark, and I want to keep the videos close to that. But the next thing that we're going to do is we're going to have to figure out how are we going to deal with the constantly changing directions that can occur as we move through space. Specifically, what I mean is how are we going to deal with the dot product analysis in comparing the angle between our two vectors if we're constantly moving around in space. So case in point, I might have some electric field lines that are pointing out in space like so, and then I decide to move from here to here. Oops, looks like my batteries are running low. I thought I was plugged into the wall. Okay, so that right there tells me I need to end the video, but this is where we'll pick up, and we're gonna have to figure out how to update this for a constantly changing direction with respect to our angles. So, see you at the next video.